All right, let's do problems from section 5.4. And the first one is kind of like number 15 in the book. Make a scatter plot of the data in the table below. So they give us a table of data, and I guess I'll go ahead and write it down on the paper. And most of this I'm probably going to do with a TI-84. I might go ahead and upload a video that shows you how to do it with the Inspire, but we've done all this kind of stuff before in class, fortunately. Well, let me write down the data points. Okay, so let's do this with the TI-84. Let's kind of remind ourselves how to do it. So remember, whenever you want to enter points into a calculator, go to the Stat key, which is right there. Select Edit. And I'm going to go ahead and clear out the list L1 first. So remember, the trick is to highlight L1 and then press Clear Enter. That'll clear out the list. Now let's go ahead and enter the data values 1 through 6 for X. And the Y values 3.5, 5.5, and so on. 6.8, 7.2. Like I said, I'll try to put up a video in Moodle that kind of reminds you how to do it with the Inspire too. Alright, but most of you do have this calculator. So after you enter all the data points, Part B says find a power function that models the data. So we want to find the best fit power function that models the data. So remember, you go to Stat and go to Calculate and scroll all the way down until you see Power Regression. And it looks like it's option A. And then I'll just press Enter. And notice that the calculator is already assuming that the X list is L1, the Y list is L2. I don't think we need to store this regression equation. So there it is. So your function looks like it's of the form a times x to the b, where a is 3.67 and b is 0.505. And it does say 3 decimal places. So that's what I get for Part A. And the rest of the problem is really very similar. Part C is find a quadratic function that models the data. Part D is find a logarithmic function that models the data. So this was actually Part B. The scatter plot is really just a visual representation of all those points. I think I'll skip that part. Part B was to find the best fit power function. Part C is the quadratic regression. But let's go ahead and do Part D. It says find a log function that models the data. So it's very similar to what I just did. Go to the Stat button, go over to Calculate. But on this one, you want to choose natural log regression, LN regression, which is option number 9. So press Enter. And again, I don't think we need to store that regression equation. So notice that the function is of the form a plus b natural log x, where a is 3.468 and b is 2.917. So that's your answer. So you can really find the best fit function of any type that's on the calculator that you want. Well, that's what I get. All right. So let's move on to the next problem, which is number 2. And I believe that's number 17 in the book. So let's look at the problem. It says use the exponential form to model the information in exercises 17 through 20. So they want us to use the function y equals a times 1 plus r to the x power. And this one says, suppose the retail price of an automobile is $30,000 in 2000 and that it increases 4% per year. So this car costs $30,000 in the year 2000. But it increases, and we're talking about the cost, 4% per year. All right. Write the equation of the exponential function that models the retail price of the car t years after 2000. So you really just have to use that equation they gave you, and I'm talking about this one. And in that equation, A is the initial price of the car, which is $30,000. And in this case, R is going to be 0.04. So R is always the annual percent increase or decrease, and X is the number of years later. And I guess in place of X, we should probably put T, because we're trying to find the price of the car after T years. So we could simplify this a little bit. That should be your answer. So notice, by the way, when T is equal to 0, 1.04 to the 0th power is just going to go to a 1, and this whole thing is just going to reduce to 30,000. So that's consistent with the fact that 0 years after 2000, the price of the car is $30,000. But let's do part B of that same problem. Use the model to predict the retail price of the automobile in 2015. Okay, so we want the price in 2015, but just keep in mind in this problem, T is the number of years after 2000. So what would T be in 2015? It would be 15. So essentially all I have to do is plug in 15 for T into that little expression right there. And I'll get 30,000 times 1.04 to the 15th power. And I'll plug that into a calculator. And I get 54,028 and 31 cents. So $54,028.34. So the price of the car went up quite a bit after 15 years because it's increasing by 4% per year. Well, let's do the next one, which is number 3. And that's really number 19 in the book. So let me read it to you. At the end of an advertising campaign, weekly sales amounted to $20,000. They then decreased by 2% each week at the end of the campaign. Write the equation of the exponential function that models the weekly sales. So this time we have something that's exponentially decreasing, but I believe we're supposed to use exactly the same function as before. But the only difference is that's going to be a negative sign because the amount is decreasing. But it sounds like it started out being $20,000 and it decreased by 2% each week. So A is the initial amount, which is 20,000, but I would actually subtract the 0.02 in this case. So if it's exponentially decreasing, you have to subtract. And I'll just go ahead and put a T there just like I did on the last problem. And I believe on the computer you have multiple choice options. But this should be 0.98 to the T power, the exponential part of that function. So that's the answer for part A. So just remember, if it's exponentially decreasing, you have to subtract that R instead of add it. Well, what about part B? Find the sales 5 weeks after the end of the campaign. Well, that's just when T is equal to 5. So let's plug in 5 for T. So this is what I get. And I guess in this case, T is in weeks. But I get $18,078.42. Actually didn't go down very much in 5 weeks. But it's only decreasing by 2% per week. So let's do the last problem from this section. And I believe this one is another calculator one. It's number 21. It says total personal income in the U.S. in billions of dollars for selected years from 1960 and projected to 2018 is given in the following table. The data can be modeled by an exponential function. Excuse me. Write the equation of this function with x as the number of years after 1960. Okay. So that's kind of an important part of the problem to keep in mind. And the data is really kind of complicated. And so this one is kind of a tough one. Or at least a time-consuming one. But let me go ahead and enter the data into my calculator. By the way, this is on page 370, and it's number 21 in the book, if you're looking. The book is also online, but I'm just going to go ahead and enter the data points to save a little time. So remember, on this calculator, let's clear out the old lists first. And again, I will try to put up a video that shows you how to do this with the Inspire 2. Well, we start out at 1960, but x is the number of years after 1960, so really the first x value is 0. And it looks like it goes by tens, so 0, and so on. So when x is 40, that corresponds to 2000. Well, the next one is actually 2008, so I believe the next x value would be 48. And then 2018, so that'd be 58. So a little tedious, but there are all the data points. So we're supposed to model this with an exponential function. So remember, on this calculator, stat, and then go over to calculate, and we should have an exponential regression. It's right there. And I'm going to go ahead and store this function because we do have a couple of other questions to answer. So remember, the way you do that is to go to variables, and then go over to y variables, function, and then just select y1. Remember, it is y1. So let's calculate. So notice once again it's a times b to the x. I guess that's something we haven't done yet in this video. And I'm just going to assume they want us to do this in 3 decimal places. So my function should look like this. So that's what I get, to 3 decimal places. Part B, if this model is accurate, what will be the total personal income in 2015? Well, just remember, the base year here is 1960, so I believe that would be 55 years later. Yeah. So I just have to plug in 55 and for x into that function. So what would be the easy way to do it? Probably to use the table. I didn't mean to graph it so quickly, but let me go to the table. So I'm just going to scroll down to 55. And I do have some y2 function in there. Let me delete that. That's probably from another problem. But it looks like I get 20,100.75. And that is in billions of dollars. But that looks about right, I suppose. It's fairly close to the data in the table. In what year does the model predict the total personal income will reach 19 trillion? So notice in part B they gave us the X value, and this one they give us the Y value. But you want to convert this to billions. But just use the fact that 19 trillion is 19,000 billion. So you want to plug in 19,000 into your calculator for Y2, essentially. So there's my function that I saved. That's the Y1 that we saved. But let's go ahead and enter the 19,000 for Y2. So this problem is kind of involved. And I might want to adjust my window a little bit. My Y max should probably be maybe 50,000. And I'm going to let my X max be maybe 100. So there's the exponential function that models the data. And there's the constant function that represents 19,000 billion, which is really 19 trillion. So what year is it? Well, go to calculate and find the point of intersection. Hit enter 3 times. And it's really just the X value that you're looking for. And I would just round to the nearest year. It looks like 54 is the nearest X value. But the answer is not 54. Remember, the base year is 1960. So you would just add 54 to 1960, which I believe would give you 2014. Let me see. Yeah, it's 2014. So in 2014, it should reach about 19 billion, or 19 trillion.